So now we're going to go ahead and deal with rose curves, which rose curves are just like the previous graphs. If you're stuck, you can always plug in values for the theta. Now, there are a lot of shortcuts that will make it a lot easier on rose curves, but I want to explain why the shortcuts work. So we're first going to talk about this graph. So this graph over here, I've just graphed r equals 3 sine of 2 theta on a rectangular plane, where r is our y-axis and theta is my x-axis. And this is 2 pi, so I'll go all the way to 2 pi, and this is pi. So this is what 3 sine of 2 theta would look like. Now, the most important thing to know is at 0, where do we start? It's always the first thing you need to know, and we know we're at 0, 0, meaning if I plug 0 in for theta, I would end up with 0 for the radius. So that's my start. Next important thing to know is where all your max and minimum values are. So those values are at positive 3, negative 3, positive 3, negative 3. And the angles, if you look at where pi is, all of these angles are just in fourths. Pi is right here, so we're splitting pi into 4 equal pieces. So the first angle would be at pi fourths, then 3 pi fourths, 5 pi fourths, and 7 pi fourths. And you'll notice if I actually plug in pi fourths for theta, 2 times pi fourths is pi halves. 3 times sine of pi halves does in fact give you positive 3. So the graph can it just helps us plug numbers in faster. Now, if you look back at this graph, in between all of these points where it's hitting the maximum or the minimum, you're hitting back at 0 as well. Okay, so we start at 0, that's our starting point. Pi fourths is 3, 1, 2, 3 right here. 3 pi fourths is negative 3, so 3 pi fourths is right here, so negative 3 is over here. 5 pi fourths is positive 3, so right here. And 7 pi fourths is a negative radius, so this one right here. So it is important to know where and when I placed all these, because one of the important things, like I said, is to know the direction you're taking your graph. So we started at this red point right here. So from there you go to the pi fourths, and it just grows quickly, then doesn't, kind of slows down the growth. So it makes it look kind of like a petal. These are why these are called rose curves. After pi fourths, you remember we go back to 0 on between each one of these. So I go back to 0. Then we're going to go to the 3 pi fourths one, which is, remember, the negative angle. So that's actually over here in the 4th quadrant. And then once again, it goes back to 0. Then we go to the one at 5 pi fourths, which would be back over here in what we consider the 3rd quadrant in the rectangular plane. And then go back to 0. And then the last one, go back to 0. Sweet. Now, I'm going to come back to the slide in a bit, but one of the things to notice is that there was an even number of petals. Each of the petals went out a length of 3. So this number will always tell me my length of my petal. The number in front of the theta, when it's an even number, you will always have 2 times the number of petals, so 2n petals. So in this case, we had 4 petals because 2 times 2 is 4. So notice if you go back to my general equation I wrote up here, the n is the number in front of theta. Okay, so that will always happen. Length will always be the first value. The number of petals will be right there. We're going to talk about where to start after I show the next one. We're going to do the cosine one, and then I'll talk about how you can tell where these start every time without having to draw the reference graph. So we got 5 cosine of theta. So if you look right here, our first value at 0 is the maximum, which is 5, which makes sense. If you remember, I told you our length is 5. So we should always max out at 5, and our minimum should always be at negative 5. Now, knowing where these next angles are, though, is important. So I'm going to go ahead and take my pi right here. And you'll notice that the pi is split up into 6 equal pieces, which means this is 1, 6, 2, 6. So this is a third. So I know at pi thirds, I'm at negative 5. This next one, so a third, that would be 2/3. I'd be at +5. Now there are a lot more because we have a few more cycles between 0 and 2 pi. So at pi, we're at -5. And at, this is, so that was a 2/3. So, and that's 3/3, or sorry, yeah, 3/3 or 1 pi. So this next one would be 4/3, which would be at 5, and so on. But I'm going to show you something before I even do the rest of them. This is what's cool about the odd petals. So I'm going to go ahead and plot my reference one. So I've got 0, 5. Pi-thirds, that's this line right here, but I need to go back 5. So I'm going to go right here, back 5. We've got 2 pi-thirds, which is also 5. And then what you're going to notice, pi is right here. I need to go back, and we've actually repeated, or I should just say they're the same as the original. So if you try to do 4 pi-thirds 5, you'll actually end up in the same spot as this one, and it just keeps repeating. So this is the same as that one. So for the odd petals, they repeat a lot quicker than for even petals. In fact, you'll notice for odd, whatever the n value is, n tells you the number of petals. You don't double them. So notice there's actually only 3 locations. It is important to know that between each of these values, once again, you're going to 0. So we're starting right here, and you start, it's positive first on the cosine. So you start at your point, and you go all the way to the positive right there. And then we're going negative, so it's going to go like so into that third quadrant in this case. And then it loops to this other one over in this second quadrant, back to 0, and then back to the start. So take note of the way it was drawn. So here's what I want to talk about with the start. Something you're always going to notice is that cosine's always going to be the easiest start. Cosine functions always start, so cosine of n theta will the length of the petal will always start at theta equals 0. And there's a reason for that. If you plug in 0 for theta, it doesn't matter what n is. So if I do cosine of n times 0, you'll get cosine of 0. Cosine of 0 is always 1, so you're just going to be taking your a value and multiplying it by 1, and you'll get the full length of the petal. Okay, so cosine will always start at 1. The sine one, you'll notice, didn't start at the same place, and if you graph a lot of sine functions, the petals will change location of where they start depending on what your n value is. That's because what we're trying to do is we're trying to figure out where n times theta is equal to pi halves. So we always start at theta equals pi over 2n. You might wonder why pi halves? Well, if you think of where sine is equal to 1, the only location on the unit circle is pi halves. And if you remember why 0 worked on the previous one, when I plugged in 0, I got cosine, or you got cosine of 0, which is equal to 1. So we're trying to find the location where it maxes out on the unit circle, and that would be pi halves. So it'll be always pi over 2n. So if you go to that previous one, using that method, I knew this one starts at pi over 2 times 2, or pi over 4, because we were dealing with sine. So I'm going to go to my last one, the single petal, which uses those same tricks. So I'm going to just do this one with the tricks. It's a single petal, which is really just an odd petal, if you really think about it. It's non-centered circles, what ends up looking like. You can draw, or you can do the table if you want. But let's go ahead and just practice that. So the petal length, let me actually start with that. The length of the petal, in this case, will be the 4. So I know I'm going to be going out 4. Because this is sine, we need to do our pi over 2n, which is just pi over 2 times our 1, which is pi over 2. So I know my one petal, there's only going to be one petal. And we know there's one petal because, oh, that was the last thing I just want to emphasize is if your n is odd, it tells you exactly, n tells you exactly how many petals you have. Once again, if n is even, you double the number of petals you have. Okay, so there's one petal. So I know I'm going out here to 4, a length of 4. We know we have to eventually get back to 0. And in fact, technically, when I say the start, that's not really the start. The start for sine is at 0, 0. You start at 0, 0, and you wind your way out to that point. And let me draw that circle a little better. And there is a decent circle because it is a non-centered circle on these ones.